Hello, welcome to meteorology class. I was pleased to get to talk to a few of you between 1 and 2 today. I'm not sure my office hours will be tomorrow. I'll establish that, put it on Power School. But with the people who were logged on, there were about 3 or 4 of you, kind of got a little ahead of where I was with the video, so they get a little bit of a repetition. You get to hear it for the first time, but I might move a little bit quickly. First of all, I was talking about the types of fog in the last video. Where did I put? There's my marker. Here's our new board. I was talking about the different kinds of fog, and we had talked about fogs formed by cooling. Let's say this is the temperature, this is the dew point. Where the temperature went over to the dew point's place, it cooled off. It could cool off by radiation. Clear night, the heat radiates off the ground out into space. Ground cools first. Air cools from the ground up. Fog forms from the ground up. Starts off knee deep, comes up waist deep, then gets maybe 100 feet deep. And that's radiation fog on a clear, fairly calm night. Then there was advection fog where, for example, maybe warm, moist air traveled over a cold ocean current, got chilled from the bottom up, forming a thick layer of fog, like maybe 1,500 feet thick, moves into maybe San Francisco. So that's advection fog, because advection means motion of air like that, the wind. And then, my dog, okay, I'll show you the dog in a minute. But then there was upslope fog, where you have a gentle slope like Kansas, gradually getting higher as you go from one side to the other, like a very, very gently sloped mountain. Remember, Misty Mountain got clouds forming on the side at the lifting condensation level. Well, if your mountain is so gentle that you don't think you live on a mountain, then you won't call it clouds. You won't say, look, we're up in the clouds today. You'll say, look, it's foggy. And that, again, is adiabatic expansion of air that's being lifted as it's lifted orographically due to terrain. Those were fogs formed by cooling, where in each case something cooled the temperature off to the dew point. The other thing that can happen is you can raise the dew point up to meet the temperature. How do you do that? One way that I was talking about, I think I got interrupted yesterday doing this. One thing is it could just rains and rains and rains, and the rain evaporates, and that raises the dew point up, and it might meet the temperature. Of course, temperature probably dropped because of the rain, so it might not be meeting all the way at the temperature's place, but they converge and they meet somewhere because of evaporation occurring. By the way, you won't really get much fog while it's raining significantly for the simple reason, I mean, you might have asked, I could ask calling somebody. I'll call on my dog. Sheba, hi. Why isn't it foggy when it rains? And Sheba says, because the rain washes the fog out of the air. Sorry, that's really stupid. Anyway, I'm just missing students. It's kind of weird talking to myself. I can see myself here. But in any case, yeah, once the rain lets up, now you can get some fog because it's all wet outside. Another thing is like you're sitting in the hot tub with the snow coming down out at the ski resort. Never done that. Bucket list thing, I guess. Maybe you've seen that. You know, you got that warm water and cold air right over it and all that evaporation happening off the warm water. Pretty soon it gets all foggy. Now, you also see this over lakes. And I wonder if you've ever noticed what time of day, what time of year you'd see that. You'd probably know it if you like to fish. I don't like to fish because I don't have the patience. I can't seem to. Maybe I just don't have the allure, you know, to get the fish to bite. So I get bored and don't do it. But I think people go out to fish early in the morning sometimes. And if they ever go out to fish early in the morning in the fall, they may be going through a little smoke over the water there. Actually, it's steam fog. It's because the water's still warm, left over from the summer, kind of like the hot tub. And the air is nice and cool because it's fall and it's in the morning. So this evaporation off the water causes a shallow layer of fog. And we'll see the wisps of it coming up off the lake. Steam fog. Now, you know what? We just learned about all the kinds of fog. Now what we need to talk about is how precipitation happens. It happens, well, basically there's condensation. I'll tell you what, there's 2 ways rain happens. Your book tells about them. I'm going to back that up. One of them is and I don't know if this is the order the book does, it might be backwards, but I like to talk about the collision-coalescence, coalescence, maybe I spelled that right, coalescence phenomenon theory, which is to say that clouds are naturally going to have different sized droplets in them. I mean, they're not all going to be exactly the same size, are they? And due to some physics about air resistance and all, the bigger droplets fall faster. So if a bigger droplet falls faster, it's going to run into little droplets. It's going to smash into them and grab them and gobble them up and become a bigger droplet. And you know what? A bigger droplet's going to fall even faster and gobble up more little droplets. Pretty soon you've got a raindrop falling through the clouds, scooping up little droplets as it goes, as they adhere to it and coalesce with it. Actually, if they get too big, they get unstable and often split in half or something. But they'll reach a pretty good size, and they're raindrops, and they come falling out of the sky. I'm glad they don't increase size without limit, because then it can be dangerous. Like you get hit by a raindrop that big, you might have a problem. But so that's how it rains, right? Clouds, little droplets get together because of different falling speeds, coalesce, rain. Well, that explains a lot of rain, but it doesn't explain all rain, because there's another way it can happen. This is the hard one. This is the one that I'm not so sure that you get it just from reading about it, so I'll do my best to explain it right quick. Checking my time, 6 minutes, okay. So the Bergeron process happens in cold clouds, clouds that are already below freezing. Now, they, of course, contain water molecules, but so does this air I'm breathing right now. You know, no biggie there. But they do contain ice crystals. It's below freezing. You can have some ice. I'll represent those little snowflake-like things. These are some ice crystals. And those have frozen in this, they have frozen, that they've deposited in this cold cloud. They actually tend to form on something called freezing nuclei. Now, water droplets form on condensation nuclei like dust and salt and pollen and smoke and whatever aerosols are in the air. But some of them are more prone to get an ice crystal from, because they got, I don't know, some kind of little jagged edges or something that help the little crystal and funny little structure, snowflakey structure get started. And so, ice crystals. But there are some naughty things in the cloud. I say naughty because they're not doing what they should. There are also coexisting water droplets that maybe weren't on a freezing nucleus. And if the number of water molecules in the droplet is fairly small, there's a pretty good chance that none of the molecules is willing to go first. None of the little groups of molecules there are willing to go first and be the ones to freeze. So they just like don't do what they should be doing, hope nobody's watching. It's called supercool water droplets. If they're small enough, they can actually exist with temperatures as low as -40 Fahrenheit or Celsius. They're equal at that point. So it's strange. You can have a mixture of ice crystals that, because it's below freezing, and water droplets. And typically the temperature is about -10 Celsius, maybe 14 Fahrenheit, or somewhere in there, to have this situation. Okay, here's the deal. These droplets and crystals are either going to grow if they get net, water molecules added to them, or they're going to shrink if water molecules leave them. I want you to think of the water droplets like drop-in parties, stop-by events. It's like open house. Come in, leave when you want to. Remember when we showed the can of water, and we had the water in there, and water molecules were shooting off at the top of it, bouncing around. But some were coming back in. Well, some were coming in, some were leaving. It's always somebody coming, somebody going. That doesn't have much net effect on the size. If more come in, it grows. If more leave, it shrinks. But not a whole lot of net difference, perhaps. Think of the snowflakes or ice crystals like parties where you can never leave. I don't know if you are familiar with the song Hotel California, but there's a line in it. One of the verses is, you can check out any time you want, but you can never leave. That's kind of what the snowflakes are like. They're like parties. You walk in, yeah, come on in. And then they don't let you leave. They lock you in because it's an ice crystal. crystalline structure locks them in. It's not that nobody could ever leave. Every now and then some water molecule might get lucky and escape from one of these, but for the most part, once you're in, whether you like it or not. So what happens to a bunch of potential party-going molecules and some little drop-by events and simultaneously some parties that you're not likely to ever leave? Well, the parties you're not like, they don't give you warning. They don't have a sign outside, you'll never leave. So water molecules innocently go in there and then they'll come out. Not many of them. So this means that the ice crystals grow explosively at the expense of the water droplets, which actually probably tend to shrink a little bit as they lose customers or partygoers. These are basically snowflakes. They're big ice crystals. They start to fall because they're heavier. They run into other things. The little things freeze onto them. They get pretty patterns and all that kind of stuff. And of course, the Bergeron process obviously creates good old snow. So the question is, which one of these things is more common? Does this mostly happen or this? Depends on where you live. If you live somewhere where all it ever does is snow, then it's always Bergeron. If all it ever does is rain, it's maybe either. I won't ask Sheba this time. I'll just say it. A lot of the rain in the world starts as snow. Very simply, it comes from way up high in clouds. It's cold up there. We learned all about that, lapse rates and all. And as it falls down and gets into warmer air, yeah, a lot of the time it melts. So a lot of the rain you've seen in your life was snow before it reached you. Not all of it. If you live in the tropics or if it's really in the middle of summer and you get a little shower, it's probably rain from the get-go. It's probably collision-coalescence the whole way. But the Bergeron process basically makes snow. Bergeron, by the way, is this Norwegian guy who wasn't feeling good, went to some resort at a ski place in Norway, where he's from, and noticed the clouds disappearing. The fog would like vanish in the forest because the trees were like freezing nuclei, and it would do like Bergeron process, and that's why it's named after him, because he figured that out. Anyway, I am now going to talk about other kinds of precipitation. Let's do that. Basically, I've just explained rain and snow. Rain forms from the collision-coalescence process or from the Bergeron process and letting it melt on the way down, whereas snow is just Bergeron. But what about that other stuff, and what other kind of stuff is there? Let's name some other kinds of precip. I'll list them. Okay, there's rain, there's snow, maybe you've heard of sleet. Now, what sleet means depends on what country you live in. In other English-speaking countries besides the United States, I'm not real sure about Canada, but in England and maybe in Australia, if they even get this, they mean, when they say sleet, a mixture of rain and snow, like rain and snow falling at the same time. I've seen that. I saw that last winter when it snowed on the north side of town and barely snowed here. I saw some rain mixed with snow. Some of the stuff coming down was rain, some of it was snow. In England, they'll call that sleet. That's not what I mean when I say sleet. That's not what people in this country mean. Sleet is little pieces of ice. They're little particles of ice. They're frozen raindrops almost. And they click. When it's sleeting outside, you can, like, it'll be like maybe raining outside, and I'm not really paying much attention to it. It's just the pitter-pat rain. And the pitter-pat turns into clickety-clack. That's sleet. And I look outside, and these little pieces of ice are bouncing off the car. I've sometimes seen it sleet so much it piled up to the ground like that thick. And it's not really snow. It's kind of funny trying to make snowballs out. It's real dense. You could hurt somebody with one of those snowballs. You can pack it together, throw it, and get sued for it or something. But so sleet is ice pellets. Ice pellets. That's sleet. But wait, there's more. There's another thing called freezing rain. Now, notice I did not say frozen rain. I said freezing rain. You see, ice pellets or sleet is frozen rain. It already froze. Freezing rain is naughty water droplets that are supposed to be frozen and just nobody wanted to go first. So they remained liquid at temperatures slightly below freezing, usually about -1 Celsius, about 30 Fahrenheit might be typical. And they don't freeze until they touch something. As soon as they touch a pine needle, a power line, a car, a bridge, just about anything they touch, they instantly, or within a fraction of a second, so fast that they hardly even have time to drip off of it. They do drip a little and make icicles sometimes, but freezing rain is nasty stuff. Freezing rain gets all over things, coats things, piles up real thick, and then tears trees down, tears power lines down. It's one of the nastiest kinds of precipitation you can imagine. I got interested in the weather because of the January 7, 1973 ice storm, and that storm consisted of an initial period of heavy sleet that piled up about an inch or so thick, and then 3 inches worth. It didn't all freeze on everything, but some of that 3 inches of rain was freezing. Froze on the branches, tore down everything. Just about I told about that. So freezing rain is nasty. There's a couple more that I'll mention. Now let me explain these first, then I'll mention a couple more. First of all, I would like you to be able to tell the difference between the situations that cause each of these. The book does talk about it, but here's my version. What we need is a picture of the profile of the atmosphere as you go up from the ground with regards to temperature. Say this is freezing. This is 0 Celsius right here. And this is height going up the side. I'm not going to worry putting how many thousands of feet, but I don't know. Maybe that's 8,000 feet. That'd be typical, 8,000 feet. If the environmental lapse rate is all below freezing, Sheba, what would that make? Snow. Whatever. That would make snow. Look, it ain't going to be, I mean, it's below freezing the whole way. It formed by Bergeron process. If it's below freezing, it's Bergeron process. It makes snow, stayed snow. You know what? It might still be snow, even if it looked like that, because maybe it just barely got above freezing and didn't have time to melt. I saw snow falling, was it last month, I guess, whenever that was, at temperatures around 36 Fahrenheit, a little bit of snow. It was kind of half melted, but I've seen snow as high as 43 or 44 degrees because it was so cold up high and it was coming down fast enough, it just didn't quite have time to melt. Usually if it's about 35, 36 as the surface, it's going to melt before it hits. But that's snow. What about rain? Rain's obvious. Rain would be like either the temperature was above freezing the whole way or it was above freezing most of the way down. You know, enough to melt. So that's rain. This is snow. We draw another diagram for other kind of things. This is a little more tricky here. Here's another one. There's 0 Celsius. Here's maybe 8,000 feet. Sometimes you might start with snow up here, or way up high. It gets into so much warm air that it melts. The snow all melts. It's falling as rain. But surprise, sometimes there's what you call a temperature inversion, where the temperature is colder near the ground. It can happen especially in Atlanta and up I-85 through South Carolina, North Carolina. We often get this thing called the wedge with this cold, shallow layer of air, and warm rain from the warm Gulf air up above rains down into this very cold, shallow air near the surface, and the temperature goes below freezing. But the raindrops don't have time, don't feel like it, whatever, don't freeze. And they come down liquid, and then they touch branches and things. And instant ice. That is freezing rain. I probably should switch colors, but my marker's in that box. I won't. I'll just draw more. That's freezing rain. One more thing can happen. You could have the same situation, but a thicker layer of cold air near the ground. Thicker and colder, like that. If the raindrops have to fall through a couple thousand or 3,000 or 4,000 feet of sub-freezing air, especially if it's well below freezing, they're going to turn into ice usually. They're usually going to freeze before they hit. And then you have sleet. So sleet is what happens when you had snow that melted into rain and then, surprise, refroze. That's why they're not snowflakes. They're frozen raindrops. And typically, they probably were once upon a time snow, and they either completely or partially melted, and then they refroze. So sometimes you have sleet falling with temperatures like this, below freezing, well below freezing, and sleeting. I've seen a big storm like that before. However, there's also the possibility, I've seen this many times, where it melts, refreezes, and can then pass back into warmer air. And I have seen sleet falling with temperatures above freezing. And it has this zigzaggy pattern in the air temperature above the profile, where it probably started as snow, melted into rain, got into more cold air, froze, turned into sleet, into ice pellets. And then sometimes those ice pellets can survive a few thousand feet of above freezing air. I've seen sleet at 50 degrees, in fact, Fahrenheit, about 10 Celsius. So these are the basic kinds of precipitation: rain, snow, sleet, and freezing rain, and the situations which they could occur. Let me name a couple more. There is some stuff called Graupel. It's German for hail. I'll talk about hail in a minute. Graupel, excuse me. I've seen it several times in my life, including one day around the end of December this last winter. I saw a little bit of graupel. It's weird. It's like snowballs. It's they're not really snowflakes. It's like you had a snowflake and it started to melt and it got partway melted, and then it kind of started to freeze again on the outside. It made this crusty little thing, kind of like, I don't know, it's probably like I'm sure there's some kind of candy like that, you know, the kind of thing where you, it's like frozen on the outside and gooey on the inside or whatever. Graupels, these little snow pellets, and they're in between snow and sleet. They're kind of like they'll sort of bounce off things, but sometimes they bust open, and they fall faster than snowflakes, but slower than rain or sleet. And again, I did see them recently. Sometimes they happen with a little above freezing. They're kind of an in-between deal. Graupel. Then there's hail. Hail can be nasty because hail can knock you on the head, hurt you. Hail can be big. I've seen pictures of hailstones this big. What is it? Well, is it just frozen rain? Not exactly. It's not as simply as sleet is. Sleet has made one trip straight down. You know, sleet came down, it melted, then it refroze. Okay, great. It's just a droplet, just one little droplet. What happens with hail, it happens in cumulonimbus clouds and thunderstorms, where you get huge updrafts so powerful that they can take a raindrop and turn it around and make it go up. And it goes riding up in this updraft. Obviously, the air is unstable. It gets carried up into the frigid regions in the upper part of the cloud, and it freezes. And so now it's a little piece of ice, and now it tries to fall. And then it gets down to where there's like rain all around. It gets a little rain on the outside, maybe. It gets in another updraft, and it goes up again, and it gets maybe super cooled water freezing onto it, because there'll be those naughty, not yet frozen droplets up there. So multiple trips in like 2, 3, even 4 updraft cells within the cumulonimbus cloud in a thunderstorm can keep coating more and more and more ice onto these things. Finally, they get out of the updraft, which was maybe 70 or 80 miles an hour straight up updraft. They get out of that, and then they fall, and then they just come flying down and smash people's crops and bust people's windshields and pile up on the ground. There's been some amazing hailstorms in history. But you realize hail is mostly a summer and spring phenomenon, because it's when the thunderstorms are roaring, you know, moving away. Sleet is a winter thing. And sleet doesn't happen everywhere, you know, not our kind of sleet. Hail, anywhere you get a big thunderstorm, you could get that. Doesn't happen much in the tropics, though, because in the tropics, the freezing level is so high, they usually can't do much of that. Severe thunderstorms, if you see hail, watch out for maybe tornadoes. So hail, nasty. Oh, there's also something called rime. All rime is, and it's not R-H-Y-M-E, it's R-I-M-E. It's this little frosty stuff that happens when freezing fog gets on things, and it cooks feathery little beautiful things of ice over stuff. I think that's all the precipitation types we need to worry about. I'm actually going to try to finish this chapter right now because there's not a whole lot left. I've talked about all the precipitation types. Let's see, chapter 555 here. There was a thing about weather modification. Oh, here's the nice pictures in the book about the different kinds of precip. See, they tell you about it too. But they do sleet, freezing rain, you got their hail. Then they talk about weather modification. You know, there's this saying, I don't know if you've heard it or not, it's like everybody talks about the weather, but nobody does anything about it. Well, I mean, what can you do? Not much, huh? Oh, maybe you've heard about attempts to do things about the weather. There's such a thing as trying to control the weather. Some ideas to control the weather are frighteningly absurd. At some point back in the 50s, somebody, I forget who, suggested nuking hurricanes, like dropping nuclear bombs into the eye of a hurricane. I doubt that would do much to the hurricane, but it sure would spread radioactive debris over a large region, so you could get your house blown down and get radiation poisoning or something. So, yeah, we don't nuke storms. There's this idea of making rain by a thing called cloud seeding. It's not a bad idea. It actually kind of works. What you do is you find a cloud that's just on the edge of it. It could almost rain, but it just doesn't have enough lift going on, not enough quite going on. And you drop freezing nuclei into it. Dry ice. What else do they drop? Silver nitrate? I forget. But there's a couple of things you can drop from an airplane into a cloud. And the stuff sprinkles into the cloud, and it makes little things get together, and you can make it like drizzle. You can make it rain a little bit, just a little bit, in one little area. It does work, sort of, but it's not the kind of thing that really ever got very far. Some places they've experimented. It is pretty good for clearing fog up at certain foggy airports. That it can do. But it's not going to save Farmer Jones, you know, crops because a cloud came over and he seeded it. Even if he did, Farmer Smith would probably sue him for stealing his rain because maybe the cloud was headed to his farm. So it doesn't get done a whole lot. Now, there is one area of weather modification that is pretty significant, and that is having to do with preventing freezing of crops like citrus crops. Oranges are very sensitive. You know, you got a nice big juicy orange. If it freezes, you know, the whole pulp in there, the pulp like freezes and it makes it all mushy and it's like barely even good for juice anymore. They probably use it for juice, but you're not going to sell that thing, you know, in the store for like just an orange after it froze. So citrus growers definitely want to keep their oranges and all that nice. So how about this for an idea? How about that? Look, you like hose them down. You get icicles all over them. Looks like the stupidest thing ever, right? It's below freezing. Would you like somebody spraying a hose on you when it's below freezing? Well, actually, if you're an orange, first of all, oranges aren't warm-blooded. They're not blooded at all, thank goodness. Though there's a kind of orange called blood orange. It's kind of reddish. But they spray water on them so that the water will freeze instead of the orange freezing. And the latent heat released, the latent heat of fusion released when the water that you spray on the orange freezes actually takes the hit. The heat, it insulates the orange almost. I mean, it's like the water on the outside makes these nasty icicles, thus saving the orange on the inside. So latent heat from freezing, literally you just spray them and hose them down. And it actually keeps the inside of the orange warmer, not colder. Outside's cold, it freezes, but it keeps the inside safe. Another thing is this nasty thing called smudge pots, where they get big tar-like stuff and petroleum things and burn it. And first of all, it's a little bit of heat in the orchard, but also it makes this big cloud of smoke, and the smoke lies all over the oranges, and maybe you have to wash them off later, I guess, maybe. But the smoke is like a cloud, black body radiation, infrared radiation. It's like a cloudy night, and it keeps it warmer. And then another one most people would think was stupid, but it isn't, is to blow a fan on everything. You run a big fan, and you might think, no, it'll be so cold for the poor oranges. But no, look, oranges, again, are not warm-blooded. They don't give off body heat that can be blown away by the wind. They don't suffer from the wind chill factor. Instead, what you're doing is you're mixing the air up, and the air near the bottom of the surface that was going to get so cold down in the orchard gets mixed with air hundreds of feet up that forgot it was supposed to be a cold night. And you mix it up like on a windy night, doesn't cool off as much. There you go. Now that's weather modification. And you know what? I mean, there's contrails we make with planes. I think I've pretty well covered this chapter, and you were completely in a good spot. Wow, those cars got smashed up. You're in a completely good spot now to finish your homework for next time. So talk to you soon. Bye.